Chapter 11. 357 sextillion, 686 quintillion, 312 quadrillion, 646 trillion, 216 billion, 567 million, 269,137 is huge. The number 357 sextillion, 686 quintillion, 312 quadrillion, 646 trillion, 216 billion, 567 million, 629,137 is a massive 24-digit prime number. But this is why it's special. If I remove the first digit, 3, from that number, the remaining number starting with the 5 is also a prime number. And if I do that again, if I remove the 5, the remaining number starting with the 7 is also a prime number. And that will be true all the way down. So up to 629,137, which is a prime number. I can remove the digit. The next number will be prime all the way down to 7. So it's always prime when I truncate from the left. So it's called the left truncatable prime. And there are finitely many of them, and that is the largest one. And I learned this from my favourite maths guy, James Grime. James is on a maths channel called Numberphile. Anyway, let's get back to it. In the image on this pad, Number Buddy 26 is holding a pencil with the number written on it. No matter how much he sharpens this pencil, he's always going to have a prime number, which I think is why he's saying, always in your prime. It's a kind of a joke. So this is a left truncatable prime. Let me show you how you can create them, because they're not that hard to create. So let's start with the last digit. So the last digit could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. My last digit could be any of those numbers, but it has to be prime as well, because I want a prime at the end. So 1 is not a prime. 2, we could have a prime 2 at the end, but that's not going to be able to be extended very much. We could have 3 as a prime number at the end. 4 we're not going to have at the end. 5 could be at the end. 6, no, not a prime. 7, maybe. 8, not a prime. And 9 is not a prime. So it's going to have to end in one of those numbers. But let's just try now to extend it back. So we're going to extend it back to the left and make a 2-digit number. Let's go from the 7. Okay, let's make a chain. Let's go from the 7. Well, if I extend it, it's going to be either 17, 27, 37, 47, 57, 67, 77, 87, or 97. So which of those are prime? 17 is a prime. 27, he's not prime. 37 is prime. 47 is prime. 57 is not. 67 is prime. 77 is prime. 77, he's not a prime. 87 is not a prime, 97 is a prime. So let me do a couple more steps. Let's go from 47 and extend her further back. 147 perhaps? Or 247? 347? 447? 547? 647? 847, 947, and we keep extending this if we want. Let's find a prime on that list. So 947 is a prime. I'll go and extend that back another step. So this could now be 1947, 2947 perhaps, 3,947, 4,947, 5,947, 6,947, 7,947, 8,947, or 9,947. I'm going to extend another step here. I'm going to go from 3,947. I know that is a prime. So I'm going to go from there next and try to extend that back just to do another step. So 3,947 could now be 13,947, 23,947, 53,947, 43,947, 53,947, 63,947, 73,947, 83,947, or 93,947. And I'm going to stop at this step because if I do the checking through, none of those are prime. This 13947 is not a prime. 23947 is not a prime. 33947 is not a prime. Not a prime. None of those are primes. So the chain stopped. The chain is terminated. So the last prime we had there in that chain was 3,947. So that's the endpoint for the chain that we had. The number of endpoints that you can make just doing this calculation. And there's 1,442 of these endpoints. So those are going to be the largest prime in the chain. And the largest one of them is the 24-digit prime number I mentioned earlier. But clearly you can see that there are only finitely many. Because once you get to an endpoint, they can't be extended any further to the left. So that's left truncatable primes. Shall we do right truncatable? Just to show you the largest one that's possible. I'll show you the largest right truncatable prime. So this is just a bit of fun, really. So it's a silly thing, I know. However, if I use a different base, because this is a base 10 thing, if I used a different base 12 or base 20 or base 100 or something like that, then each step would have longer lists. And if the list is longer, that means they're more likely to hit a prime. So you're going to end up with longer chains. You actually end up with bigger left truncatable primes if you do it in a larger base. For right truncatable primes, the largest one we have is 73,939,133. So if I start removing digits from the right hand side, I'll always have a prime. If I allowed 1 to be a prime, we could have a larger number. We could have this number, 1,979,339,339, which is a prime number. And if we remove digits from the right, we'll always have a prime number. But we end up with 1, and 1 isn't a prime number, so I don't know why I've even mentioned him. Let's have a look at left and right truncatable primes. Is there a prime that's on both lists? And yes, there is. The largest one of those that we can find is 739,397. So that's left truncatable and it's right truncatable, so it's on both lists. Although I don't think we can truncate simultaneously, because we're not going to get prime numbers if we do that. What's the longest you can do simultaneously? Well, that's a good question. Because what about if I can remove digits in any order I want? 415,673. And I'm going to delete, not just from the ends, I'm going to delete the 1. There, he's gone. So now I've got 45,673, and that's a prime number. Now I'm going to delete the 3. So now I've got 4,567. Now if I've got that, I'm going to delete the 5 in this case to get 467, which is a prime. And now if I remove the 4, I make 67, which is a prime. Now I think I'll delete the 6 to get 7. So I create a chain of primes, but I'm allowed to delete the digits any way I want, so those are called deletable primes. And it is thought that there are infinitely many of those. But that is something we don't know because we haven't proven that to be true, so that is a challenge. What's the number you can create a deletable prime? Well, it doesn't matter what digit you delete. Any digit you delete will still leave you with a prime number. Well, that's another good idea. I don't know if they exist. That would be interesting to find out.